Hello everyone. So today we will start a new unit, second unit of this fluid mechanics, that is fluid statics. Now what is fluid statics? So as the name suggests, the study of forces which are acting on the fluid which is at rest. The study of forces on the fluid at rest is nothing but fluid statics. Okay, so when we are talking of the fluid which is at rest, suppose we are having a fluid at rest, and if I consider a small element, a small particle of this fluid, so what are the forces acting on this particular element of the fluid? So basically there are two types of forces acting on this static fluid. The very first type of force is the body force. This body force is nothing but external force. Okay, body force means the force which is acting throughout the body, throughout the mass of the body is called as body force. For example, the gravitational force acts throughout the mass of the body, that is body force. Electrostatic force, if the fluid element is in influence of electrostatic field, then the electrostatic force will act. If it is in influence of magnetic field, then the magnetic force will act. So these are the body force which are acting external, which are acted upon by the external means. So these are called as the body force, or you can call it as external force. Okay, second type of force is the surface force. Okay, and this surface force is because of the influence of this fluid with the other neighboring fluid. Okay, so this is basically an internal force. Getting this? So two types of forces: body force, which is by external means; surface force, which is by the fluid elements, other fluid elements only. That is why it is called as the internal force. Okay, now this internal force, this surface force can be either a normal force, as we know, normal force, that means the force which is acting perpendicular to the surface is called as the normal force, and second is the shear force. Shear force acts along the surface of the element, that is shear force. Okay, so two types of forces: body force, surface force. In surface force, further this can be either a normal force or this can be a shear force. Okay, obviously because this fluid is in rest, this is a fluid at rest, so obviously no frictional force will act because it is at rest. Second thing, because this element, only compressive force will act in this element and not any tensile force, because the pressure will be acting. Pressure is always compressive in nature, so only compressive force will act in this particular fluid element and not the tensile force. Getting this or not? Now let us consider a small tetrahedron particle, an infinitesimal small tetrahedron particle of this fluid, and analyze the forces in it. So we are considering a small tetrahedron particle of this fluid, okay, and we will analyze the forces on this particular fluid element. Okay, so this is our tetrahedron element. Okay, so these are the four faces. First is AOB, which is coinciding with plane YZ plane. Second face is AOC, which is coinciding with XZ plane. Third plane is OBC, which is coinciding with XZ plane. AOC coincides with XY plane. OBC coincides with XZ plane. Okay, and last phase is ABC, which is obviously inclined to the axis. Getting this? Okay, so suppose the stresses acting on this faces are, suppose in x direction, suppose the stress acting is sigma x. This sigma x is acting on AOB plane, perpendicular to AOB plane. Similarly, sigma y acting perpendicular to OBC plane, and sigma z acting perpendicular to AOC plane. These are three stresses. Now apart from this, we have one more plane, ABC. So in this ABC, suppose sigma n is acting. So this sigma n is actually perpendicular to ABC, first thing. And let's suppose the sigma n is making an angle alpha, beta and gamma with x axis, y axis and z axis respectively. Okay, because this sigma n is perpendicular to this plane ABC, and this is suppose making an angle alpha with x axis, beta with y axis and gamma with z axis. That means their component in x, y and z direction, if I want to determine, so those component will be cos alpha, cos beta and cos gamma. Clear or not? Okay, now because this is fluid at rest, So obviously acceleration is equal to 0. So now applying equilibrium equation, summation of Fx is equal to 0. So this will give us what? Summation of Fx, total forces in x direction. So this will be sigma x into this area, the shaded area AOB, which is nothing but half into dy into dz, okay, minus sigma n. Now this sigma z will have no component in x direction, sigma y will also have no component in x direction, only the sigma n will have a component, and the component, as I told you, will be equal to sigma n into cos alpha into the area. Okay, so this will be sigma n cos alpha into the area of, suppose ABC is suppose dA into dA, this should be equal to 0. Getting this one? Suppose this is equation number 1. Similarly, summation of Fy is equal to 0. Okay, so this will be sigma y into half dx dz minus sigma n cos of beta. Okay, now apart from this, a weight is also acting. The weight of this tetrahedral will also act in downward direction. Okay, and what will be the force, what will be the stress because of that weight? So this will be equal to minus the volume is dx dy dz divided by 6 root 2, okay, into g into rho, this should be equal to 0. Okay, the stress because of the weight, sorry, the force because of the weight. Getting this should be equal to 0. This is suppose equation number 2. Similarly, summation of Fz is equal to 0. So here again sigma z into half dx dy minus sigma n cos of gamma should be equal to 0. This is equation number 3. Okay, now from all these three equations, one thing we can conclude, that this sigma n into this dA into cos alpha. What is this dA cos alpha? dA cos alpha is nothing but the projected area of this ABC on YZ plane. dA cos alpha is nothing but projected, because this angle, this sigma n is making an angle alpha with x-axis. So the perpendicular, that means ABC, will make this ABC plane will make an angle alpha with y-axis. Okay, so this dA, if I project this dA onto this YZ plane, I will get the same area as AOB. Getting this? This AOB is nothing but the projected area of ABC on YZ plane. Similarly, this AOC is nothing but the projected area of this ABC on XZ plane, and this BOC is nothing but projected area of ABC on XZ plane. Getting this? Okay, so this dA cos alpha is nothing but this area of AOB, which is nothing but half into dy into dz. Getting this or not? Okay, so further this equation can be written as what? dA cos alpha is nothing but half dy dz. So this is half dy dz, this is also half dy dz. Half dy dz will get cancelled out, and we will get what? Sigma x is equal to sigma n. Getting this? Similarly, from equation 3, sigma z is equal to sigma n. And similarly from equation 2, because this is a very, very small element, as we have considered this as infinitesimal small element, so the weight of this infinitesimal small element can be neglected. Okay, and further this will also be sigma y is equal to sigma n. Now this is a very, very important conclusion. Now the stresses acting on all the planes, from all the directions on a fluid element which is inside a fluid at rest, the stresses acting on from all the directions is same, and this law is nothing but Pascal's law, and this was discovered by Blaise Pascal. This law is Pascal. So Pascal's law, what is Pascal's law? If we are considering a fluid element at rest, the stresses acting from all the direction on that particular fluid element will be same. Okay, as I told you, suppose this is our fluid element. This is our fluid element. If I am considering the fluid element here, now the stresses, or you can call it as the pressure force, the pressure acting from all the direction on this fluid element will be same, provided this fluid should be at rest. Okay, so the pressure acting from all direction is same, and this pressure, as I told you, we call it as hydrostatic pressure. We have already discussed this in strength of material. If we are, suppose we are having an element, okay, in which the stresses acting in all direction are compressive and the magnitude and direction of the stresses are same, then such stress is called as the hydrostatic stress or hydrostatic pressure. Okay, so the Pascal's law say, Pascal law क्या बोलता है, if we are having a fluid element inside a fluid at rest, so the forces acting from all the direction on that particular fluid element will be same. The not forces, the stresses acting or the pressure acting from all the direction is same. This is called as the Pascal's law, and that pressure is called as the hydrostatic pressure. And how will be the Mohr circle? So the Mohr circle, as we know, because the stresses are equal in magnitude and equal in direction, and the direction is compressive, so obviously the Mohr circle will be a point. This also we have seen in the strength of material. So the Mohr circle will be a point. So if a fluid is flowing, if a fluid is obeying a Pascal's law, then the Mohr circle of that fluid element at a particular instant is nothing but a point. Getting this now? Okay, so as we have seen, the Mohr circle for the fluid which is following Pascal's law should be a point, because the pressure acting from all the directions is same. And Mohr circle is a point, that means the shear stress should be equal to 0, that means tau is equal to 0, and we know what tau is equal to mu into du by dy, that means this mu into du by dy should be equal to 0. Okay, so now coming to the validity of this Pascal's law, when will the Pascal's law will be valid and when the Pascal's law will not be valid. Okay, so the very first case for a static fluid, if the fluid is stationary, for a static fluid, since du is equal to 0, okay, and since this du is equal to 0, therefore tau is equal to 0, therefore for stationary fluid the Pascal's law is valid. Okay, क्योंकि देखो दो चीजें हो सकती है, tau is equal to mu into du by dy, so either this mu should be equal to 0 or this du by dy should be equal to 0. So if the fluid is a static fluid, then obviously this du by dy is equal to 0, that means whether this mu should be equal to 0, whether this mu is equal to 0 or not equal to 0, in both the condition this du by dy is equal to 0, therefore tau should be equal to 0. Okay, so this Pascal's law is valid for both ideal as well as real fluid. Okay, why am I saying this ideal and real fluid? For ideal fluid mu is equal to 0, for real fluid the mu has certain value, but because this du is equal to 0, so this tau is equal to 0, so this Pascal's law is valid for the fluid, static fluid. Okay, now for fluid in motion, okay, so for fluid in motion, in this the first case is for ideal fluid. So if the ideal fluid is in motion, tau is equal to mu into du by dy. Okay, so if the fluid is an ideal fluid, then obviously this mu is equal to 0. Okay, so this tau should be equal to 0. Shear stress will be equal to 0. That means Pascal's law is valid. Okay, so when we have the ideal fluid, whether the fluid is stationary or whether the fluid is moving, in both situations Pascal's law is valid. Okay, now what about in real fluid? Second condition for real fluid. Okay, and in that the first case for rigid body motion. Real fluid for rigid body motion. Rigid body motion means the fluid is moving like a rigid body, like this. That means the velocity at all points is same. Okay, so this is an ideal case which is actually not possible. The fluid cannot move in, cannot have a rigid body motion, because as we have already discussed in first unit, that the velocity of this fluid changes like this. Okay, but here we are assuming that this is a rigid body motion, that means the velocity at all the points of the fluid is same, then we can say that the fluid follows the rigid body motion. Okay, so in case of rigid body motion, because the velocity is not changing, that means du is equal to 0, and since du is equal to 0, whether it is a real fluid or whether it is an ideal fluid, this tau should be equal to 0. Getting this? That means again Pascal's law is valid. Pascal's law is valid. Getting this now? Okay, so in which cases Pascal's law is valid? First, when we have the static fluid, du is equal to 0, therefore Pascal's law is valid. So second, when we have the fluid in motion, so in that the first case is when we have an ideal fluid which is in motion, since mu is equal to 0, so the Pascal's law is valid. Okay, now for real fluid, this mu is not equal to 0. Okay, so for real fluid, this mu is not equal to 0, but in this case, for rigid body motion, since du is equal to 0, therefore tau is equal to 0 and Pascal's law is valid. Okay, now second case, for non-rigid body motion, okay, non-rigid body motion means the actual motion like this. Okay, so here we will have certain value of du, and tau is equal to mu into du by dy. Okay, and since this is not an ideal fluid, this is a real fluid, this mu will be greater than 0. Also this du by dy will be greater than 0, therefore tau is not equal to 0, therefore this does not follow Pascal's law. Getting this or not? Okay, so if we have a real fluid which is following non-rigid body motion, then this will not follow the Pascal's law. And as I told you that whenever it is following the Pascal's law, the Mohr circle will be a point. Okay, now coming to the pressure and its measurement. Okay, so pressure, as we know, is force per unit area. What will be unit of pressure? The unit of force is Newton, unit of area is meter square, so unit of pressure is Newton per meter square, or you can call it as Pascal. Okay, another unit of pressure is bar, and this 1 bar is 10⁵ Pascal. Okay, another unit of pressure is Newton per mm square, or you can call it as megapascal. Newton per mm square is nothing but megapascal. This is Newton per meter square. If I convert this meter square into mm square, it will be 10⁻⁻6 mm square. This 10⁻⁻6 will go up and it will be 10⁻⁶ Newton per meter square. That means you can call it as megapascal. Okay, so this will be 10⁻⁶ Pascal. So this is the pressure and its unit. Okay, so now we will look into some of the applications of Pascal's law, and the most common application of Pascal's law is the hydraulic press. Hydraulic press is used in the hydraulic cranes, or if you have seen the hydraulic lifts, the same principle of Pascal law is used. Okay, so suppose, how is it possible, have you ever wondered that how is it possible that by applying just a small force we are able to lift a heavy force through cranes or through lifts? We are just applying a small force, and in result we can lift a very heavy force. So how is it possible? So I will tell you this thing. So suppose this type of arrangement is there, and inside this we have a fluid. Okay, and here the weight is kept, the weight which is to be lifted is kept here is suppose 100 kilonewton. This is 100 kilonewton of weight is kept. Getting this? The diameter of this, here we have the diameter as d, the diameter here is d, and here the diameter is 10 times of d. Now why we are taking this as multiple times of this diameter, you will understand this soon. Okay, and here we have to apply the force, and by application of this force F, we have to lift this weight of 100 kilonewton. Okay, so how much this force will be acting? So let us understand this thing very carefully. So we have this fluid, and according to Pascal's law, as I told you, that the pressure acting on this fluid will be equal from all directions. Okay, so we have suppose the pressure acting which is acting here will be same as the pressure acting here, but the area here is less and area here is more. Okay, so the pressure is same, that means suppose this is 0.1 and this is 0.2, so the pressure will be same, that means P1 will be equal to P2. Okay, now P1 will be equal to force per unit area, so this will be F by area is pi by 4 into small d square. This is equal to P2 which is 100 kilonewton, force is given is 100 kilonewton divided by area is pi by 4 into 10 d square. Getting this? Okay, so from here this pi by 4 d square will get cancelled out and this 100 will also get cancelled out and we will get what? F is equal to 1 kilonewton. Okay, now amazing thing that just by application of 1 kilonewton of force we can lift up to 100 kilonewton of this weight. Okay, this is the application of Pascal. So this principle, as I told you, is used in the hydraulic lifts, in hydraulic cranes, wherever you want to apply a small force and you want to lift the heavier weight. Now coming to very important thing, that is differential equation of pressure intensity at a point. Okay, so let us consider a small fluid element of dimension dx by dz, dx in x axis and dz in z axis, and y axis dimension is taken as suppose 1 unit. If you want, you can take the y axis dimension, ultimately it will be cancelled out. Okay, and at the center the weight of this element is acting suppose dw and the pressure at this point is dp. Okay, and with respect to x axis suppose the pressure is changing and with respect to z axis suppose the pressure is changing. So what we have to determine, how much pressure will change with respect to x axis and with respect to z axis. Okay, so suppose the rate by which it is changing is dp by dx. Okay, so the pressure here at this point, this will be dx by 2, this distance is dx by 2. Okay, so the pressure at this particular point will be p plus dp by dx, okay, into dx by 2. Okay, dp by dx is the change in pressure with respect to distance, unit distance. Okay, so we will multiply it by distance into dx by 2 into, this is pressure, into, if we want to determine the force, that force will be equal to into area, and area is nothing but dz into 1, the thickness is 1, so this will be into dz. Getting this or not? Okay, similarly at this particular point, at this point the pressure acting will be P minus dp by dx into dx by 2, here will be less pressure, into dz into unit distance 1. Getting this? Okay, now similarly with respect to z axis also this pressure is changing, so here we have the pressure as P minus dp by dz into dz by 2 into, the distance is dx into dy, area is dx into dy, dy is 1. Again here P plus dp by dz into dz by 2, dp by dz into dz by 2 into dx. Getting this? Okay, so this is how the pressure will be acting in this particular fluid element, a small fluid element. Okay, now for equilibrium, summation of fx should be equal to 0 and summation of fz should be equal to 0. Okay, so putting summation of fx is equal to 0, so this will be P minus dp by dx into dx by 2 into dz minus P plus dp by dx into dx by 2 into dz, this should be equal to 0. Okay, so from here this p dz this will be cancelled out. Okay, now this will be dp by dx into minus dx by 2 minus dx by 2, dx by 2 plus dx by 2 is dx into dz, this should be equal to 0, or you can say this dp by dx should be equal to 0. Now what does this mean? This is a very important thing. dp by dx is equal to 0, that means the pressure is not changing with respect to x axis. Okay, that means at same level at all the points, at same level the pressure will be same, pressure is not changing with respect to x axis, first thing. Okay, now what about with respect to z axis, with respect to height, whether the pressure is changing or not? Let us consider this. Okay, so now here we have what, summation of Fz is equal to 0. Okay, so here P minus upward forces dP by dz into dz by 2 into dx, okay, minus P plus dP by dz into dz by 2 into dx. Okay, now downward force is this also, weight minus dw. Okay, and this dw can be written as specific weight into volume, and volume is what, dx into dz into dy. Dy is 1, so this will be specific weight into dx into dz. This should be equal to 0. Getting this or not? Okay, so from here this pp will get cancelled out, and finally we will get what, minus dp by dz is equal to gamma. Okay, this is the second result. Okay, and from here we can conclude one thing, what, that with respect to z axis, with respect to height, the pressure is changing. Okay, so the pressure at same level at all points will be same, but with respect to z the pressure is changing. Suppose this is equation number 1. Getting this or not? Okay, now here with this gamma, as we know, is the specific weight which is equal to rho into g. Clear or not? Okay, so we have seen what, minus dP by dz is equal to gamma, or dP by dz is equal to minus of gamma. Okay, now let us suppose we have two different points, this is point 1 and point 2, and at point 1 the pressure is P1 and at point 2 the pressure is P2. So the pressure head at point 1 is P1 by gamma. Okay, pressure head is P by rho g, P by gamma, and the pressure head at point 2 is P2 by gamma. Okay, now how that pressure head comes, we will discuss that too. Okay, now we want to determine the equation for this, the relation we want to determine. So this dP will be equal to what, minus gamma into dz. Okay, now if I integrate it between the 2 points, so this will be integrated between P1 and P2, and here this will be integrated between Z1 and Z2. Okay, so if I integrate it, I will get what, P2 minus P1 is equal to minus gamma into Z2 minus Z1. Okay, or you can say P2 by gamma plus Z2 is equal to P1 by gamma plus Z1. Okay, this is nothing but this P by gamma is nothing but the piezometric head, P by gamma plus Z. Okay, so this P by gamma plus Z is nothing but piezometric head. Okay, so one thing is clear, that at any point the value of this piezometric head will be same, whether you can take this at any point, the value of this piezometric head, which is P by gamma plus Z, this piezometric head is same at all the points. Getting this not? Okay, so you can write the note here, for a static fluid piezometric head remains constant throughout the fluid. For a static fluid piezometric head remains constant throughout the fluid. Okay, now coming to another conclusion from this equation, from the same equation. So now what if I want to determine the pressure at height h? So pressure at height, or you can say at depth h. Suppose we have this fluid surface, and at a depth h we want to determine the pressure at this particular point. Okay, so we know what, dP by dz is equal to minus of gamma, or you can say dP is equal to minus of gamma into dz. Okay, now if I integrate it from 0 to h, okay, or from h to 0, sorry, from this point to this point, from h to 0, so this will be dP is equal to minus integration, sorry, plus integration 0 to h gamma into dz. Okay, so this P will be equal to gamma, which is rho g, and integration of dz is h. Okay, so this pressure at a height h is nothing but rho g h. Getting this one? So if you want to determine the pressure at any height h, directly you can put this formula, P is equal to rho g h, and remember one thing, this is a gauge pressure. If I want absolute pressure, I will have to add atmospheric pressure in this. We will come to this. Okay, but the pressure at any height h is equal to rho g h. Now what is this pressure? Suppose we are our earth is surrounded by a 64 kilometer, approximately 64 kilometer layer of atmosphere. Okay, now we are at this particular point. Okay, so this much air is exerting this force, this pressure, a continuous pressure on our body. Okay, and this pressure is nothing but the atmospheric pressure. This is nothing but atmospheric pressure. So this atmospheric pressure, if I want to determine, this will be equal to rho gh. Getting this on? That means if I take this much height into rho into g, I will get the value of this atmospheric pressure. Okay, so as I am getting deep and deep into the fluid, that pressure will increase. Since this P is directly proportional to H, so as I am going deeper and deeper inside the fluid, this pressure will increase. So the pressure distribution will be like this. Getting this not? Okay, so this is very important conclusion. P is equal to rho g h.